Hello and welcome to the Shell Scripts for Beginners course. My name is Mumshad Manambat and I'm with Vijin Palari and we'll be your instructors for this course. Shell scripts in Linux are an easy-to-use, time-saving solution for automating repetitive or complex set of tasks in a system administrator's daily life. It can help save time and increase productivity, so it's a must-have skill for anyone working on computers. Shell scripts can be used to automate repetitive tasks such as perform daily backups of your system or installing and patching packages on multiple servers or monitoring the system periodically such as to check the memory, CPU, and disk usage and raise alarms if required. Or perform regular audits on a system such as to identify logged in users, monitor their activities, or to identify processes consuming most resources, or search through multiple log files and identify root cause of problems. This course is a beginner level course and is for those who are absolute beginners to shell scripting or programming. System administrators or IT engineers who do not have any prior programming experience can go through this course to gain basic knowledge of shell scripting. As part of this course, we will explain the necessary programming concepts required for shell scripting. And we will learn in a fun way using examples of a space station launching missions to explore the universe. We will also see a number of real-world use cases of scripts throughout this course. Our embedded hands-on labs will make sure you gain enough hands-on practice right after you learn each concept. We will test your scripts to make sure that you have written them correctly, and we will also provide feedback. This course is divided into different sections where we discuss what shell scripts are and how to get started with your first shell script. We discuss how to make your scripts executable. We discuss various concepts related to scripting such as variables, control logics such as conditional statements, loops such as for loops and while loops, and arithmetic operations, etc. And throughout the course, we will also discuss best practices while scripting, such as what to do and what not to do and how to develop a script that's reusable. We will also see some tips and tricks such as some IDEs and utilities that can help you improve your scripting skills. As a prerequisite, you must have basic Linux knowledge and command line experience. These are covered in the Linux Basics course on our platform. And I reiterate that there's no programming knowledge required for this course. Let us get introduced to our project for this course. You're going to launch rockets into space using shell scripts. No kidding. You're part of the team responsible for orchestrating rocket launches to space, and you decide to do it using shell scripts. You're tasked to develop a script that automates the launch sequence. Before writing any shell script, it's important to know the in and out of what you're trying to automate. You don't want to get the sequence or the operations wrong while launching a rocket, as it may result in a catastrophe. So here's how the sequence works. First, start the auxiliary power, then switch to internal power, followed by the auto sequence start, and then start the main engine, and finally lift off. Pretty simple. Now you don't need to know rocket science to execute these steps to launch a rocket. The rocket scientists have been very resourceful in creating commands that you can run to launch a rocket. So like your usual Linux commands such as ls or user add or mkdir, which or directory, etc., you now have commands specific to rockets. For example, to start the auxiliary power, run the rocket start power command. To switch to internal power, run the rocket internal power command. To start auto sequence, run the rocket start auto sequence command. To start the engine, run the rocket start engine command. And finally, to lift off, run the rocket lift off command. Now you will be launching multiple rockets into space. So to list all rockets, run the rocket list command. To create a new rocket, run the rocket add command. To destroy a rocket, run the rocket delete command. And to get the status of a launched rocket, run the rocket status command. And in case of failure, we can use the rocket debug command to see the reason of a failure. Before starting to develop your script, it is important to have a clear idea on what you are developing it for. You must write down the exact steps and associated commands required to complete your task. Let's quickly go over our requirements based on what we accomplished in the previous lab. We first created a directory for our mission. We named it Lunar Mission. Then we created a rocket for that mission, and using the rocket add command, we then followed the launch sequence by running the commands for launching the rocket. And finally, we tested the status using the rocket status command to make sure the launch was successful. For each mission, you'll have to follow the same steps of creating a directory and then running the sequence of commands to launch the rocket. You decide to automate it and make it simpler using shell scripts. To create a shell script to perform all of these tasks, we create a file named create and launch rocket, and we move all the commands to this file in the same order that we executed them in. It's important to name your shell scripts so that it makes sense. In this case, since I'm first creating and then launching a rocket, I will name it create and launch rocket. This will allow yourself and others using the script in the future to know exactly what the script does. We will also give it the extension .sh to indicate that it is a shell script. Now that's the simplest form of creating a shell script. We can now execute the script using the bash command. When a shell script is executed, it runs each line in the script one after the other until all lines are complete. If one of the command takes a long time to execute, it will wait until it's finished before proceeding to the next line. There are different ways to execute a shell script. We saw one way in the previous slide, which is using the bash command. You can also configure a shell script to run like any other command on your system as an executable, such as create and launch rocket.sh. This way, you can create your own executable commands on your system by simply developing shell scripts. Now, if you plan to do this, then it is a best practice to not name your script with the .sh extension, because you don't typically see commands in Linux with a .sh extension. This way, it looks more like a command. However, if you try to run it now, you'll see an error that says command not found. We have only created the script, but we haven't really configured it as a command. We haven't told the operating system that we intend to run this script as a command or where this script is located. Whenever a command is run on a Linux system, the operating system looks at the paths configured in the path environment variable to locate the executable or script for that command. If it can't find the command in any of these paths that are listed here, the command not found error is thrown. To add our script as a command, append the path to the directory containing the script to the end of the path variable like this. Now, a better way to do that is to specify the $path variable instead of the existing entire path. That way, you don't have to type in the entire contents of the existing path. And you can also prevent accidentally making a mistake while typing in that existing path. Now, once this is done, you will be able to run the script without having to provide the path like any of the other built-in or external commands that we saw earlier. To see the location of a command, run the which command followed by the name of the command you'd like to see the location of. In this case, running the which command and specifying the create and launch rocket command lists the location of our script, which happens to be in the user Michael's home directory. For a shell script to work, we must set the correct permissions to the file. After creating the shell script file, running the file for the first time will result in a permission denied error if the permissions are not set correctly. This is because the execute bit needs to be set for the file to be considered as an executable. If we inspect the file permissions using the ls-l command, you can see that the X bit is not set for this file at all. We can add that using the chmod command and make it executable. Here we will make use of the chmod +x command followed by the script name to make it executable. We learned about the execute bit and file permissions in the Linux Basics course. So if you're not sure about this, go back and have a quick look at it. Now, if we run the script, it works. So let's look at some best practices. When developing a script, always give it a name that makes sense. A good way to go about this is to imagine what another person would understand when looking at your script. So names like script1.sh or myscript.sh or test.sh are bad examples. Also, if you plan to make your script an executable to be run like a command, then you may leave out the .sh extension. However, it is a good practice to keep the extension if you don't plan to make your script executable like a command. Let us now look at variables in shell scripts. The script we developed performs all the steps we needed to do. However, we see that we have the name of the mission, which is lunar mission, hard-coded into each line in the script. Now that's not a good practice for multiple reasons. One, if the script were to be modified in the future to add a few additional steps, you would need to make sure that you use the same mission name on those lines as well. A small typo with the mission name while doing that on any of these lines may lead to unexpected results. Secondly, if we were to use the same script for another mission, then we would need to go through the entire script and modify all the lines of code that has the mission name in it. For example, if we were to use the same script for a mission to Mars, we would need to modify each line in the script to update the mission name to Mars mission. And there are chances of errors during that activity as well. A variable is a value that can vary or change. In this script, the values that can change are the mission names, so we replace the hard-coded mission names with a variable named mission_name. But how do you differentiate a static value from a variable? A variable always has a $sign before its name. In this case, it's $mission_name. We must now set the value for the variable at the beginning of the script. However, remember that while setting the value of a variable, we do not use the $sign before the variable name. Next time we plan to use the same script for another mission, all we have to do is replace the mission name in the first line with the name of the new mission and no changes to be made to the rest of the script. Also note that a variable name may only contain alphanumeric or underscores. So mission_name is okay, but mission-name is not okay. And it is case sensitive as well. So uppercase mission name and lowercase mission name aren't the same. We saw how the value of a variable is set to the mission name. You can also use variables to store the result of another command. For example, the rocket status command outputs the status of the launch as either launching, success, or failed. We can store the output of the rocket status command in a variable and then print a message to the screen using the echo command and replace the variable to display the status of the launch. As you see here, you can use the variable anywhere within a string to show the value as part of the string. When naming variables, follow the best practice of using lowercase only and with underscores to separate words. Here are some good and bad examples. Let us now look at command line arguments in shell scripts. Our script is now easy enough to be used for different missions. In its current state, we can execute the script to create and launch a rocket for a mission. For a new mission, we modify the script to update the new project name and then run the script to create and launch a rocket for that mission. We repeat the steps for each new mission. Now, having to edit the script to change the mission name each time isn't very convenient. What would be convenient is a way to specify the mission name in the command line itself when we launch a new mission. Something like this. That way, we never have to modify the script ever again. So how do we do that? We can specify the mission name on the command line. But how do you access the mission name that was specified on the command line from within our script. If we could somehow get it all the way here, where we have currently hard-coded the mission name, then that would solve our problem. Now, from within a script, you can access the command run by the user using a special set of built-in variables. The command run by the user is split into multiple parts, and each part is stored in a built-in variable starting with the number 0. The command itself, which in this case is create and launch rocket, is available at $0. The second part of the command, which is our mission name, is stored in a built-in variable named $1. And in case we had other parts for the command, it would go as $2, $3, $4, etc. These are called as command line arguments. So in our case, we can replace the hard-coded mission name within our script with the built-in variable $1. So going forward, for all missions, we can simply call the script and pass in the name of the mission as a command line argument and never ever have to modify the base script ever again. So here we are assigning one variable the value from another variable. The variable mission_name gets the value from the variable $1. So there are two variables. Is that really required? No. So here's another version of the same script. You could get rid of the mission_name variable and simply use $1 in all places instead. So we now only have one variable used in our script. However, in the future, when you or someone from your team reviews the script, they may not understand what $1 stands for. So it is recommended to do it the first way by assigning the value to a meaningful variable name and then using that variable name throughout the rest of the script. As a best practice, always make sure you design your script to be reusable. Always develop the script keeping in mind that it is to be reused by another person who has not developed the script or probably don't even have experience working with shell scripts. Your script shouldn't require modification each time before it is run, so it shouldn't have hard-coded variables inside the script. Instead, use command line arguments to pass in inputs. Let us now look at prompting for inputs in a shell script. We saw one way of passing in an input to the script by using a command line argument of $1. That way, when the user runs the script, they pass in the mission name as part of the command. Now say for instance, what if we want to prompt the user for a mission name when the script starts instead of passing in the mission name as a command line argument? Something like this. The script should wait for the user to type in a mission name, and then when the user types it in, use that value as the value for the variable mission_name. For this, we use the read statement. Use the read command followed by the variable name into which the value is to be stored. When the script executes, and once it hits the read statement, it will wait for the user to type in the input. Once the user types in the mission name, it will be stored in the mission_name variable. However, you see it does not prompt the user for the mission name as we wanted it to. It just shows a blank space. So another user who may be using the script may not know what to input at this point. For this, we can add a prompt for the user using the -p option before specifying the variable name. Within the prompt, we add the message to be printed for the user, and when we run the script, now it waits for the user to enter the mission name. On entering the mission, the value for the mission name is stored in the mission_name variable, and the script executes successfully. Okay, so when it comes to the two types of implementations, one is using the read statement as in the first case, the other one is using command line arguments as in the second case, which one should be preferred? Now, if the script you are building is a simple script which will be used mostly independently, then it may be okay to use the read statement to ask the user for the input. So that means the script will always require a manual intervention. And it is okay to use it for programs that require manual intervention, like asking for a confirmation from a user before deleting a file or before rebooting a server, or asking an option from the user while you develop a mini-driven program. However, as we discussed before, when you build scripts, you must design your script to be repurposed. So if this script was to be used in the future to work with other scripts, for example, where other scripts would call the script to perform a particular task, then it may be better to use the command line arguments. That way, when the other scripts call the script, they can simply pass in the mission name as a command line argument and not have to wait for a manual intervention. The scripts should be developed in a way that it shouldn't require any manual intervention unless absolutely necessary. Or a third option is to have both. First, check if the mission name is available as a command line argument. If so, use that. If not, prompt the user for a mission name. But how do you configure your script to behave in two different ways based on the inputs? Well, that's what we will discuss in the upcoming lectures when we discuss about control statements and conditional statements. Let us now look at arithmetic operations in shell scripts. Let's look at the basics of arithmetic operations. There are different ways of performing arithmetic operations in shell. One is using the expression command run as expr. You can provide an expression as input and it outputs the result. For example, here the expression is to add two numbers and it outputs the result as 9. However, note that the operator and the values must be strictly separated by a space. Similarly, you can use the expr utility to perform other mathematical operations like subtraction, division, and multiplication. However, note that in case of multiplication, you must escape the star symbol with a backslash like this. This is because star is a reserved regex character in shell and it typically means everything. So you must escape the star symbol here using a backslash. These can be used with variable substitution as well. Say for example, we have two variables a and b with values 6 and 3. Then we can use the variables instead of the numbers using the $a and $b syntax. Another way to perform arithmetic operations in Bash is to use double parentheses. The double parenthesis helps in performing arithmetic evaluation as you would in programming languages like C. Here, we encapsulate the expression inside a double parenthesis prefixed with a dollar symbol. You must either assign this operation to a variable or use echo to print it to screen. Otherwise, a shell will try to execute the output of this operation and give you an error that 9 is not a valid command. So we use echo here. Within the parentheses, we no longer need the dollar symbol prefixing a variable, and we no longer need to separate the operator and the variables with a space. And for multiplication, we no longer need to escape the star operator with a backslash. You may also use programming language C style manipulation of variables, for instance, ++a to increment a variable and -a to decrement a variable. Note that a++ and a-, works just like in C, where the value of the variable is returned first and then incremented or decremented. Note that both expr and double parentheses only return decimal output. They do not support floating point numbers. For example, if you try to divide 10 by 3, then they return 3 instead of 3.33, which should be the accurate answer. So for this, we use another utility called as the BC utility. It works as a basic calculator in Linux. It works in an interactive mode by default where you type in an expression and it outputs the results. However, you can feed input to it using echo and the pipe character like this. Note that you must use the -L operator for the utility to generate floating point results. Let us now look at conditional logics in shell scripts. In the last line of the script, we run the rocket status command to test the status of the script. Now this command returns the status of the rocket which could be one of the following: launching if the launch is in progress, success if the launch is successful, and failed if the rocket crashes and the mission is failed. Now, if the launch failed, we must check why it failed. For this, run the rocket debug command and it will tell exactly why. We now have a requirement to modify our script to take this into consideration. So we add the rocket debug command to the end of the script. However, we only want it to run if the rocket status is failed. If the launch is successful, we don't want it to run the debug command. We want our script to behave differently based on a condition. And so we use a conditional logic. Using a conditional logic, we can define whether to run a line of code in the shell script based on a condition. For that, we use an if statement. The if statement is written just like how you would say it in real life. If a condition is met, then do something. The if block starts with the if statement in the first line, followed by a condition, which we will see in a moment, followed by the then statement, under which you will specify the lines that you wish to run if the condition is met, and then the block is closed by the fi statement. Fi is obviously if in the reverse order. The if block starts with the if statement and ends with the fi statement. Now, every block opened in a shell script has an associated closing statement like this. You will see this pattern of using a keyword such as if to open a block and the reverse of that keyword such as fi to close the block in various different blocks in shell scripts. Let us now look at the condition. The condition of an if statement is encapsulated under a pair of square brackets. Within the square brackets, we must define the check to see if the rocket status is failed. We run the rocket status command in the previous line, and we also have the output of the rocket status command stored in the rocket status variable, so that's convenient. Within the condition, we perform a check to see if the value of rocket status variable is failed, and we can get the value using the $sign like this. When the script is now run, it starts from the first line and executes the commands line by line. When the if statement is reached, the script compares the value in the rocket status variable to see if it is equal to failed. If the launch was successful, the status is not failed, so the condition is not met. If so, the commands within the if block are not run. If the launch is failed, then the condition is true and the script proceeds to execute the commands within the block. You can also add an else if statement within the if block. It's not called as else if though, instead it's called elif. This way, if the first check fails, it performs the second check, and if that is successful, executes the commands within that block. Now remember, the second condition is only checked if the first condition was not true. And finally, you can add an else block at the end that will be run if none of the above conditions are met. Now let's take a closer look at the comparison statements. Now note that the comparison statement should be within square brackets, and there should be at least one space between the brackets and your statement, as well as between the operator and the values on either side. The equals operator is only to be used to compare strings, as we compared the rocket underscore status variable earlier with the string failed. To check if the status is not equal to failed, we use the not equals operator. To compare numeric values, use the -eq operator. To check if two numbers are not equal, then use the -ne operator. To check if a number is greater than another one, use the -gt operator for greater than. And similarly, to check if a number is less than another one, use the lt operator. Now there's another way of specifying a conditional operation, and that's using double square brackets like these. These work similar to the single pair of square brackets that we have just seen, except that it's an enhanced version and supports additional operations like matching patterns using expressions, and they are a bash extension, so only works in bash or other supported modern shells. The first example here checks if string 2, that is BC, is within string 1, ABCD. The star on either end of BC means that there could be anything on either side of it in string 1. The string ABCD contains the string BC, so it evaluates to true. Note that when you specify the pattern, you must not put them inside double quotes like this. The second one is also an example of pattern matching, where we check if the string ABC matches the pattern specified on the right, where the first two characters are A and B, but the third character could be C or D. That's why C or D is within a pair of single square brackets. So both these conditions would be true. However, the next one, where the third character is E, would return false because it's not either C or D. The last two operators match the sort order, so these only work within square brackets. Now these are not greater than or less than symbols that can match numbers, as you would expect. Instead, these compare the position of these strings if they were sorted alphabetically. Say we were to sort both of these strings in an alphabetical order and we number their positions, then this operator matches the position of that string after it's sorted. So BCD would come after ABC. So ABC would have a position of 1 and BCD would have a position of 2 when they are sorted alphabetically. So 1 is not greater than 2, so this would return false. In this case, 1 is less than 2, so this would return true. Let's look at and or operators. So say you have two conditions and you need to check if both of them are or either of them is true. For this, we use the and or operators. So to check if both conditions are true, use the double ampersand sign between the two conditions like this. And to check if either one is true, use the double pipe symbol like this. So this is for and this is for or operator. So this is how you would do it if you were using the single square bracket format. If you were using the enhanced double square brackets format, then you could use the and or operators within a single pair of double square brackets like this. So in this case, you don't need to separate the two conditions into two separate pair of double brackets. You could do it within a single one. Okay, so here are some examples to check if a value is greater than 4 and less than 10. That's the first one. And here's an example of a check where we are checking if a value is greater than 4 or less than 10. So there are some file level operators as well. For instance, the -e operator checks if a file exists. The -d operator checks if the given path is a directory. The -s operator checks if the file has a size greater than 0. The -x operator checks if the file is executable. And the -w operator checks if the file is writable. Let us now look at loops in a shell script. We have now built our script to easily launch a rocket for a mission with a single command. We are now tasked to launch hundreds of such rockets to different planets and stars, and for each mission, you'll have to run the same commands one after the other 100 times with different mission names. We now have to automate the automation script itself. For that, let's develop another script. We will move all of the tasks into our new launchrockets.sh script. And within the new script, instead of calling the create and launch script multiple times, we replace it with a single call, but within a for loop. Now, if you ever have to run the same command multiple times, then a for loop is your friend. Here, you want to say for every mission in the list of missions given to you, run the create and launch script. So a for loop is written like this. The first line says for every mission in a list of missions, followed by the do and done keywords. The do and done keywords indicate the start and end of the block. every command within this for loop block, that is between the do and done keywords, are run each time the loop executes. The list of missions can be simply provided as a list of names separated by space. The for loop will execute as many times as the list of mission names specified here. But wait, the create and launch call within the for loop still has the value set to lunar mission. This means no matter how many times the loop runs, it's always going to launch the lunar mission, which is not what we want. We want it to launch separate missions each time based on the list we have provided in the for loop statement. So how do we replace the value lunar mission with the correct mission name each time the loop executes? The mission variable in the for statement contains the value of the mission name for each iteration of the loop. So all we have to do is replace the hard-coded mission name, which is lunar mission, with the variable mission like this. The first time the loop runs, the value of mission variable is set to the first value in the list, which is lunar mission, so it launches the lunar rocket. The second time it runs, it is set to Jupiter mission. The third time, it is set to a Saturn mission, and then the satellite mission, and then the lunar mission 2, followed by Mars, and finally the Earth mission. So no matter how many missions we want to run, this for loop will just work fine. Now, when the mission names are too many, like hundreds or thousands, it may be hard to type all of those in within our script. So instead of hard coding all the mission names on this line, you may have to read it from a file. So we store all the mission names in a file. Let's call it mission-names.txt. And then we can replace the hard-coded mission names in the for loop with a command to print the contents of the file mission-names.txt. But remember to encapsulate the command within a pair of backquotes like this. This time when the script is run, before the for loop is run, the cat command is executed to print all the mission names, which is then used as an input to the for loop. Going forward, all you have to do is update the mission names in the mission-names.txt file and not have to touch the script at all. That's one best practice that you must follow. Always try to develop your script in such a way that no one will ever have to modify the script in the future for executing. Those without the knowledge of shell scripts should be able to run your script without even opening it. All the inputs should be either passed in to the script as command line arguments or through an external input file as given here. Another best practice is to not use backticks for specifying a command. Instead, use the $brackets expression like this. This format is easier to read and has an advantage when you plan to embed multiple commands, that is, commands within commands. So we saw two ways of iterating over values in a for loop. One is getting values from a file, as we just saw. Another way is to simply specify the items separated by a space, as we saw earlier. And now say, for example, I wanted to generate mission names from 1 to 6. So I could use a loop like this. This will generate mission names from mission 1 to mission 6. Now, if you need to run the loop 100 times, then there's an easy way. You could specify a range using the sequence expression like this, using a pair of curly brackets with a starting point and ending point of the sequence you'd like to generate separated by 2 dots. That way you don't have to type in all the way from 1 to 100. Now, if you're familiar with other programming languages, like where you write a loop with an initialization statement, a condition, and a step, like as you would do in programming languages like C, then that is also possible. For that, use a double parenthesis like this. Now, you would typically use a for loop when you have to repeat tasks many times. For instance, run a command or a set of commands multiple times, or iterate through multiple files, or iterate through lines within a file, or iterate through the output of a command, etc. Here are some real-life examples of a for loop. So here we iterate through a list of files from the output of the ls command, and then print the count of lines on each file using the word count utility. Now here's another example of a for loop that iterates through a list of packages stored in a file and installs them one by one. And here's another example of a for loop used to SSH to a list of servers and check their uptimes. But you must make sure that for this to work, you either have set up like a passwordless SSH, then it would work well. Otherwise, you'll have to type in the password for each server every time. Let us now look at while loops. Our script is now intelligent enough to give us the cause of the failure using the rocket debug command if the status is failed. Now, as we have seen, the rocket status command may return one of the three stages: launching, success, or failed. The state of the rocket may remain in a launching state for some time until it succeeds or fails. For a few seconds, the rocket continues to be in a launching state. The way our script is currently set up, it checks the status only once right after liftoff. There is a possibility that it may be stuck in a launching state for a while, after which it may fail. And since we only check the status of the rocket once, it is not guaranteed that we catch the failures all the time. Currently, we do not consider the state where the status is launching. So we need a way for the script to wait after it checks the status, and if it turns out to be in a launching state, we want to continue to check the status more times until it is either successful or failed. Now for this, we add a new condition before the failed conditional statement to check if the status is launching. Now if it is in a launching state, then we wait for a few seconds and check again. To add a wait, use the sleep command. Now after it sleeps for 2 seconds, we run the rocket status command to check the status again, and we record the status to the same rocket_status variable. But how do we check to see if it's still launching after 2 seconds? For this, we use a conditional statement again. So we now have an if statement within the if statement where we are checking the status of the rocket. If it is still launching, then we sleep for another 2 seconds. But what happens after that 2 seconds? So we use an additional conditional statement. So we now have an if statement within the if statement within an if statement where we are checking the status of the rocket. Now, if it is still launching, then we sleep for another 2 seconds, and that goes on. So this approach, as you can see, is not a good idea. What if the rocket takes a lot more time to finish the launch, like maybe an hour or 2? Now you'll be writing a never-ending set of if conditionals in your script. So you need a better solution that works all the time. No matter if the rocket takes 2 seconds or 2 hours to launch, your script should always work. Now, all of these if conditional blocks can be replaced by a single while loop. The while loop takes a conditional statement, the same one that we used for the if block, and the set of commands to execute are within the if block defined by the do and done statements, just like the for loop. So the while loop works just like the for loop, except that it executes the loop as long as the condition is true. Now with the while loop, our script is simple and will always work. When the script is now executed, it runs each line in the script, and when it hits the while loop, it checks if the status is launching. If it is not, it will skip everything under the while loop and proceeds to the if conditional. However, if it is launching, then it executes the commands within the while block. The first command is sleep, so it sleeps for 2 seconds, then checks the status of the rocket again and stores it in the rocket status variable, after which it goes back up and checks the status again. If it's still in a launching state, it goes back into the loop and waits for another 2 seconds before checking the status again. And it continues to do that until the status is not launching. Once the status changes to not launching, which in this case is failed, it breaks out of the loop and proceeds to the rest of the script. So you would typically use a while loop when you have to execute a command or a set of commands multiple times. But unlike a for loop, you're not sure how many times the loop must run in advance. The loop must run until a specific condition is met. In our example, it was until the launch was successful or failed. We didn't know if the launch would take 2 seconds, 10 seconds, or 2 hours. Now, as long as the launch is in a launching state, we want the script to wait. The while loop is also typically used to create infinite loops or menu-driven programs. So here are some real-life examples. Here's a while loop that runs infinitely because the condition is set to a static value of true. Now within the while loop, we print a simple menu which has three options. The first one is to shut down the system, the second one is to restart, and the third to exit the menu-driven program. We then read an input from the user to a variable called choice using the read statement that we saw before, and then we check the status with a set of if statements. If the choice is 1, then we shut down the system, and if it is 2, then we restart the system, and if it's 3, we run the break statement. Now, the break statement in a loop, whether it is a for loop or a while loop, breaks the program out and exits the loop. This can be handy when working with infinite loops like this. Another similar statement is the continue statement. Instead of breaking out and exiting the loop, the continue statement takes the execution back to the beginning of the loop. So in this case, if a user inputs, say, a number that is not 1, 2, or 3, then it goes here into the continue statement, and when it hits the continue statement, the execution goes back all the way to the beginning of the loop. Let us now look at case statements in shell scripts. In the previous video, we saw how to use a while loop and an if conditional block to create a menu-driven program. Now, our focus in this lecture is on the if block that we wrote to handle different user choices. The if conditional block with a lot of if and else if statements can be written in a better way using case statements. A case block starts with the case statement and ends with the ESAC statement, which is the reverse of the word case. So just like if, where we start with the if statement and stop with the fi statement, case starts with the case statement and ends with the ESAC statement. Now on the case statement, we specify the value or a variable that you would like to check for. And within the case block, we add the different cases and the associated code for each case like this. The value in the variable choice is compared against each value or pattern specified within the block before the right parenthesis. Now if none of it is a match, then it will always match with the star at the end. So that's kind of like the else block in the if statement. Now each block within the case block, which are these, must end with the double semicolon as shown here. Now our code is so much more simpler and readable than the if block. Now a better style to write this code is to separate the semicolons to a new line like this. If you have experience with programming languages like C, then the case statement is like the switch statements. Now with the case statement, the full version of our menu-driven program now looks like this. It's so much more simpler and easier to read and easy to manage.